Subatomic particles, they're literally the building blocks of everything you see, everything you touch, your entire world. And yet for most of us, they're a total mystery. Today, we're going to peel back just one layer of that mystery and look at their most basic property, their size. And trust me, what we find might just flip your whole view of the universe on its head. So, let's dive in. On the surface, it seems like such a simple question, right? Something you could just type into a search bar and get a straight answer. But as you're about to see, down in the weird world of quantum physics, the simplest questions, well, they have the wildest answers.
Think back to science class, right? You always see those pictures of atoms, little balls zipping around a nucleus, like tiny planets. We're trained to think of particles as microscopic marbles. But what if I told you that entire picture, that model of tiny little balls, is just completely wrong? It's time to unlearn what we think we know.
Okay, so first things first, let's dig into why this seemingly simple question is actually a real mind-bender. And right away, we hit our first major hurdle. As the brilliant physicist Janet Conrad puts it, we have to define what we're talking about. I mean, what does small even mean? Are we talking about how much space something takes up, or are we talking about how much it weighs?
Okay, check this out. It's a great way to think about it. Imagine you have a big, fluffy cotton ball and a tiny little metal ball bearing. The cotton ball is physically way bigger. It has a huge diameter, but it weighs almost nothing. The little metal ball, on the other hand, is tiny, but it's super heavy for its size. So which one's smaller? See? The answer completely changes depending on if you're asking about its physical size or its mass.
All right, so to even begin to untangle this, we've got to get our terms straight. We need to know what kinds of particles we're even talking about.
Okay, so first up, there's a huge difference between just any old particle and what we call a fundamental particle. Like, take a proton. You might think it's tiny, but if you smash it hard enough, and I mean really hard, it'll actually break apart into even smaller things called quarks. A fundamental particle, though, that's the end of the road. It's the absolute bedrock. As far as we know, you just can't break it down any further.
So all these fundamental particles, they basically fall into two big families. You've got your fermions. Those are the matter particles, the stuff like electrons and quarks that actually build things. And then you have the bosons, which are the force carriers, like the photons that make up light. It's kind of like fermions are the bricks that build the house, and bosons are the mortar that holds it all together. Okay, you with me? We've talked about what small can mean. We've defined our particles. Now we get to the absolute heart of the matter. The answer to what's the size of an electron is one of the most mind-blowing, completely counterintuitive things in all of science. Seriously, brace yourself for this. So, our best theory for how all this stuff works is called the Standard Model of Particle Physics. It's been tested like crazy, and it's ridiculously accurate. It's the rulebook for the subatomic world. And according to this rule, they have zero size. I'm not kidding. Zero. It means they have no physical dimensions. No width, no height, no depth. Nada. Asking if an electron is bigger than a quark is like asking what's north of the North Pole. The question just doesn't make sense. So this is a huge mental leap we have to make. As physicist Juan Pedro Otoaritu explains, they're just zero-dimensional points. Basically, stop thinking of an electron as a tiny little speck. Instead, picture it as a cloud of probability. It's not a solid thing, but more of a haze, a region where the particle is most likely to pop into existence. There's no it at the center. Okay, so if these things literally have no size, how in the world can we compare them? How can we say one is smaller than another? Well, physicists are pretty clever. They found a workaround. If you can't use size, you use the other definition of small we talked about, mass. And to measure that mass, they use this unit of energy called an electron volt, or EV for short. And this is where Einstein's famous E = mc squared comes in. It tells us that energy and mass are basically two sides of the same coin. So if you can measure a particle's energy, you can figure out its mass. Pretty neat, huh? So let's put it to the test. What happens when we measure the electron this way? We find its mass is about 0.51 mega electron volts. Now, that's a crazy small number, obviously, but the important thing is it's not zero. It's a real, tangible value that we can actually use to compare it to other particles. And this is where things get really cool. Get this. Even though an up quark and an electron both have zero physical size, when you look at their mass, the up quark is more than 4 times heavier than the electron. Isn't that wild? And just like that, we have a way to talk about one being bigger than the other, not in size, but in mass.
Okay, so after all that, we are finally ready. We have our new measuring stick, mass. So let's answer the original question. Who are the real contenders for the smallest particle in the universe? And here are our champions. In the force carrier corner, the bosons. The winner is the photon, the particle of light. As far as we can tell, it has absolutely zero mass. It's massless. Then, in the matter particle corner, the fermions, our champion is the sneaky, super elusive neutrino. Now, we know it has some mass, but it is so ridiculously tiny, it's less than 1/1,000,000th the mass of a single electron. I mean, that is just next level small. So let's take a step back. What's the big takeaway from this whole deep dive into the super small? We kicked this off with what felt like a simple question, and we ended up having to completely rethink what size even means. So in the end, what's the smallest particle isn't a trick question. It's just a question that forces you to be incredibly precise. The answer you get depends completely on how you frame the question. Are you asking about the massless photon or the unbelievably light neutrino? And that's a lesson that applies to pretty much all of science. You have to know exactly what you're asking. And this leaves us with one last, kind of mind-bending thought to chew on. Everything you see and touch, the device you're watching this on, the chair you're sitting in, even your own body, it all feels so real, so solid, right? But now we know it's all built out of these fundamental bits that are nothing more than zero-dimensional points, just ripples in a cloud of probability. So if the very bricks of reality have no size, what does that say about the house? What does that mean for reality itself? Kind of makes you wonder, doesn't it?